So here we have a problem where we have two objects rolling down a ramp, a disc and a hoop. It's a solid disc. And the ramp is 13 degrees. They give you the masses and the radiuses of the different objects, and they start to roll from rest and roll without slipping. And they want us to calculate the linear acceleration of the center of mass of the disc as it rolls down the ramp. All right, so we're going to do this using Newton's laws of motion, Newton's second law for rotation and for translation. So I'm going to draw a little sideways picture of our disk. So it's on the ramp like that. Now, to figure out that acceleration, we need to know what forces are acting on it. This object is gonna accelerate linearly and rotationally. That linear acceleration is going to be down the ramp, of course, and that angular acceleration is going to be clockwise from this point of view. So the forces we got on there's gravity, which acts straight down from the center of mass. It's important that we locate these forces at the point that they apply so that we can determine the torque that they apply to this disk that's going to result in this angular acceleration. Now there's a couple other forces. There's going to be a normal force, which I'll put in red here. It starts from there where it touches the ramp and acts perpendicular to the ramp. So it passes right through that center of mass. That's our normal force, which I'll just call N. Then there has to be friction. For an object to roll down a ramp, it's got to have static friction, actually. So that friction is going to be up the ramp. It's got to be static because it's not sliding. The bottom of it doesn't actually move at the instant it touches, at the moment at which it's contacting the ramp. It is stuck there, and then the disc rolls forward because of that. So there is no sliding, so that's static friction up the ramp. No friction, and it would just slide down without rolling at all. It would just translate right down and never spin. So since there is friction, this is going to spin. Since it's rolling without slipping, we know that that friction is static friction. So there's the forces we have on it. We know it's going to accelerate linearly and it's going to accelerate angularly. So we're going to apply both forms of Newton's second law. So translationally, if we add up all the forces on this object, we will get the acceleration of the center of mass, the linear acceleration of the center of mass as it moves down the ramp. Those forces are, so we have some angle theta here. It says 13, but I'm going to leave everything in terms of symbols right now and see how this simplifies. So that's also this angle right there. So since my acceleration is down the ramp, I'm going to choose an axis that is down the ramp. Make that my positive x-axis. And an axis that's perpendicular to the ramp. We'll make up my positive y. And this angle here between the weight and the negative y-axis is equivalent to this angle of the ramp. So from that we can see we've got a component of gravity down the ramp and a component of gravity into the ramp. The one causing the acceleration, which is on the x-axis, is this component of gravity. So that's mg. It's opposite that angle, so it's mg sine of that angle, and that is the angle of our ramp. Up the ramp we got friction, so minus the static friction. And I'm just going to leave that as Fs. I know static friction is mu s Fn, but we're going to leave it like this for now and see if we need to do anything more. All right, really can't solve anything there. We want to find that linear acceleration. want to find this A. We need to know Fs. The problem here is if we do Fs is equal to mu Sn, well that's not always true. Fs is less than or equal to mu Sn, and I don't even know mu s. It doesn't give me any mu. I just know it rolls without slipping, so I know whatever this is, it's big enough so it doesn't slip, but I don't know the mu, so I can't use that to find it. So I'm going to have to find it some other way. So let's look at the rotation application of Newton's second law. If we have the torques around the center of mass, that will equal the inertia about the center of mass times the angular acceleration around the center of mass. Now when we look at this, we've got three forces: gravity down, normal force up perpendicular ramp, and that friction. But only the friction applies a torque around the center of mass. It's the only one offset. The normal force, its line of action passes through the center of mass, so it applies no torque. The gravitation, it comes from the center of mass. Its net effect of all those atoms is as if it's at the center of mass. So it applies no torque. The only thing applying a torque is the friction, which is perpendicular to the radius. It's tangent to that disk, so that angle right there is 90 degrees, and it's one radius away. So that torque is only the torque due to the static friction. And the inertia of a disk, right, we're doing the disk, is 1/2 mr squared alpha. Now that torque due to that friction is the lever arm, the radius, which is x, which is the r. I'm just going to call it r. It's the r of my disk. It's the force of static friction, and it would be sine 90, since the angle between that r and that f is 90 degrees. That, of course, is going to be 1. That's 1/2 mr squared. Now I don't want alpha, I want a. But since this rolls without slipping, I know that a of that center of mass is going to equal alpha times r. That happens when you have rolling without slipping. So likewise with velocity is omega r, and displacement is delta theta r. So instead of this alpha, I can rearrange this for alpha. That's a over r. So I can put a over capital R. It's the r of the disk. That's the r of the disk. This is the r of the disk. Look, we got all these r's. They all end up reducing. This r takes one of those, and this one takes the other one. They all reduce to 1. So I end up with Fs equals 1/2 ma, and that's the a of the center of mass. All right, I'm just going to pop that Fs in there, and I think we're good. So we've got mg sine theta minus 1/2 ma equals ma. Now that half is the only thing left that lets us know this was a disk. If we had solved the hoop, we would have put a 1 there. It would have been just mr squared. If we had done a solid sphere, it would have been 2/5 mr squared. If we'd done a hollow sphere, it would have been 2/3. That fraction out front is the only remnant of the fact that this is a disk. Nothing else here really tells us that it's a disk. But notice all these m's are going to reduce, and we're going to get, we get gene sine theta is going to equal a plus 1/2 of a, 3/2 a. So we get that the a is equal to 2/3 g sine theta. Notice, no mass. Does not depend on mass. Nor r. Didn't depend on how massive the disk was, didn't depend on how large the disk was, only depended on this half that it was a disk. It only depends on the distribution of the mass, which is the disk shape. If it was a hoop, it would be a 1 in there. And when we put the 1 in there, we'd find that the acceleration is less. It would be half g sine theta. If it was a sphere, we'd put a 2/5 in there, solid sphere, and we'd get a different acceleration due to that. So different objects rolling down ramps roll differently, not due to their mass or their radius, but due to the distribution of mass that results in this certain fraction in front of its inertia equation. I hope that helps you with the problem you're doing. It's an interesting result. We'll talk more about that in class, but rolling down a ramp, it does not depend on mass or radius, or actually even on inertia. It depends on distribution of mass. It depends on the function of the inertia, not on the value of the inertia itself. Thanks.